The vast number of stars in the Milky Way is far surpassed by the number of microbes in a handful of soil. Each microbe is a biological factory, converting biomass into materials that microbes use. Synthetic biology puts these biological factories to work, making the materials that people use, like polymers, fuels, and pharmaceuticals. At the core of biology is DNA, the genetic code living organisms read as instructions for making materials. Much like computer programmers encode digital information with zeros and ones, DNA encodes information in 4 characters: A, T, G, and C. Making new materials with microbes starts with writing new DNA code quickly and accurately into the cell. Based in the San Francisco Bay Area, Amyris, a biotech company, partnering with Darpa, is encoding DNA to create high-performance materials to meet the needs of a growing world.
This is the vastness of chemistry that goes on inside a living cell. This is sucrose. Yeast is programmed to take sucrose and through a series of chemical transformations, make that sucrose into ethanol. Each one of those transformations, that pathway, is encoded entirely in the DNA. So if we want to make something a little more interesting than ethanol, these hydrocarbons down here, we need to recode that DNA so that it's not making ethanol, but rather making the hydrocarbons. If you can do that, you can get to the efficiencies needed to provide these new materials for the things we use in everyday life.
Working with Amyris, the DARPA Living Foundries program has increased the speed of programming microbial DNA by more than 10 times.
So why is speed and accuracy so critical? Well, consider this programmable device. It can do a lot of things. We can program a lot of functionality into this. Now imagine the only way to program functionality into this device was using these punch cards. With DNA programming, we are just beginning to get out of the slow, imprecise programming that we've had into direct programming of DNA into the microbe for the functionality that we want.
Using Amyris's Thumper software, scientists code new DNA instructions for a microbe's genome into a computer.
Even a few years ago, it would take me months of time in the lab to build the next strain. Now, this is how I do genetic engineering.
Using Thumper, we're able to translate our ideas using a special programming language into DNA in only weeks.
And the software then translates those instructions into real instructions for the robots in the lab to translate those ideas into actual microbes that they can then test and get data back from.
Rapidly encoding DNA into a microbe dramatically expands the possibility of new materials that can be manufactured. When a microbe reaches commercial targets, production can be scaled up to millions of liters. Under DARPA's Living Foundries program, Amyris developed an innovative technology for assembling DNA code into instructions. The ligase cycling reaction, or LCR, doubles the speed at which new DNA code can be written into thousands of DNA instructions. All of this new DNA code must be proofread to ensure that it is written accurately. Amyris has developed a new technology to proofread DNA code so that any errors are efficiently eliminated. In the past, new lines of DNA code could only be proofread one line at a time. Now, multiple lines of new code can be proofread in parallel by placing each line of DNA in a tiny droplet and moving it through the editing process using sound waves. These droplets are simultaneously fed into a next-generation sequencer that reads all of their DNA code at the same time. The result is a high-throughput pipeline to proofread the thousands of lines of new DNA code that are written by engineers every week. Finally, multiple lines of DNA code can be simultaneously written into a microbe's genome using advanced CRISPR protocols. This further improves the speed of DNA programming by a factor of 6. These advanced technologies, developed under the DARPA Living Foundries program, are leading the synthetic biology industrial revolution that drives a $350 billion bioeconomy. Quickly and accurately coding DNA into microbes opens the door to a bio-based future in which the possibilities for new materials are virtually infinite.